All right, so in the last section, we ended with the ideal gas law equation and the combined gas law equation. So we're going to now look at some examples of word problems using those two equations. So here's our first example. So I'm going to ask in the question, what is the temperature in Kelvin of a 1.3 mole sample of a gas at 758 millimeters of mercury in a 28.2 liter volume closed container. Okay, so there's my question. Now, when you're trying to analyze what to do with such a question, what you want to do is you want to sort of look at the question and try to figure out what's going on there. So you notice that we're looking for temperature. We don't know what temperature is. I would like to get temperature, and I would like to get it in units of Kelvin. I have 1.3 moles, so that's my number of moles. And the pressure is 758 millimeters of mercury. How do I know that's pressure? Because pressure is in units of millimeters of mercury. It's not like liters or something like that. It's millimeters of mercury, so it must be pressure. I also have 28.2 liters, and liter is a unit of volume, so there's my volume. So I look at what I have, and I notice that I don't have two temperatures, I don't have two pressures, I don't have two volumes. And it also doesn't say anything is constant. So that means that all of these are in play, and you only have one of them. So that must mean that you must be using the ideal gas law. So let me go ahead and write out the ideal gas law. So the equation that we're going to use to solve this problem is the ideal gas law, PV is equal to nRT. After you write out PV is equal to nRT, let's also, and you notice after I write this, that there's my temperature, there's my number of moles, there's my volume, and there's my pressure. So I'm looking for temperature. There's the temperature that I'm looking for. Okay, so I have everything covered. So I've got everything except temperature. So I've got moles, I've got the units of, I got the number for R, I've got pressure, I've got volume, and I'm looking for temperature. Okay, so there we are. Let's go ahead and write out the number for the value of R. So R is equal to 0.08206 liter atmospheres per mole Kelvin. Okay, so we've got the equation, and we have one of the numbers already squared away. All right, so let's look at the word problem and try to figure out what P is. So I already wrote down that P is that. So I'm going to say pressure is equal to 758 millimeters of mercury. Don't forget to write out the units, because if you have the wrong units, you will get the wrong answer. And if you don't write it down, you'll forget. So we wrote down 758 millimeters of mercury for the P. All right, according to my equation, the next thing I need is V. And I already sort of pre-labeled that this is volume. And I know it's volume because it has units of volume. So you got 28.2 liters of our gas. Now, we already wrote down what R is. I also have N, so I've got N is equal to 1.3 moles. How did I know that that was N? Well, it said moles. And then we have R. So when we look at our equation, I can see I've got P, I got V, I got N, I've got R. The only thing I don't have is T. and I'm looking for T. So there you are. I've got my equation all done. So all I'm going to do is plug everything into the equation and then just solve for T. Now before we do that, we want to take a look at the units of our R. So R is in units of liter, atmosphere, mole, Kelvin. The volume in liter is good. We're okay with that. The volume of the mole is good because that's moles. And we're looking for temperature in Kelvin, so you don't even have to convert it after we get the temperature to get Kelvin. But we've got units of pressure here in millimeters of mercury, and we need to have units of atmospheres. Why? Because if we don't, what will happen is that when we try to plug in the R, and we have pressure in millimeters of mercury, and the R is in units of atmospheres, it's not going to work. It's not going to cancel out. So we have to convert from millimeters to atmospheres. We're not going to convert in the opposite direction. We're going to go from millimeters to atmospheres. Now, how are we going to go from millimeters to atmospheres? Well, we won't go back to the very beginning of our talk when we had pressure units. So we have this equation for pressure units. So you got 1 atmosphere is equal to 760 millimeters of mercury is equal to 760 torr, and you got 758 millimeters of mercury. So we're actually going to use this to convert from millimeters of mercury to atmospheres. So you know the standard old dimensional analysis idea where we are going to multiply by 1, and the 1 is going to have the same thing on top as on the bottom. So we're going to say 760 millimeters of mercury on the bottom, and we're going to say 1 atmosphere on the top. Now, why did I put the millimeters of mercury on the bottom? Because if I put millimeters of mercury on the bottom, it will cancel out, and then I'll end up with units of atmospheres for that number. So when I go ahead and do that, I'm going to end up with, for my pressure, the value that I end up with is going to be 0.997 atmospheres. And don't forget to write out the units, because if you start leaving out the units, you'll get confused, and then your number will come out totally incorrect, and you'll lose points. Okay, so now we're going to plug everything into our word problem. Now, there are 2 ways that you can do this. You can go ahead and solve for T based on the symbols and then plug in, or you can plug in and then do the algebra with all the numbers all plugged in. If you are good with algebra, I would suggest that you go ahead and do the algebra and then plug in, because if you do, then it's easier to work with because you don't have to carry lots of numbers and units around. But there is a possibility that after your algebra might be all messed up, and then you'll plug in the numbers, and then everything will be all messed up. So my suggestion is, if you're doing a word problem where you get partial credit for doing things partially correctly, my suggestion is go ahead and plug it in, because then I'll look at what you plugged in, I'll look at your equation, and then from there to coming up with a correct algebraic answer, there is not much points going from everything, all the chemistry done, everything plugged in into the equation correctly, and then a little bit of algebra mishap between you having plugged everything in correctly and coming up with a final correct answer. So my suggestion is plug everything in before you do your algebra. Okay, so let's go ahead and plug everything in before we do our algebra. So we're going to plug in P, so we're going to say 0.997 atmospheres, and then we have 28.2 liters. Our number of moles is 1.3 mole. I also suggest that you write all the units down. And then we have R, which is 0.08206 liter atmosphere per mole Kelvin. And then we have T, and we're solving for T. All right. So we're going to do a little bit of algebra where we end up with the final T. So whatever you do to the left side, you also do to the right side of the equation. And we would like to have T by itself. So if I want T by itself, we're going to divide both sides of the equation by 1.3 mole and 0.08206 206 liter atmosphere per mole Kelvin. So we're going to divide both sides by this little part right here. Okay, so let's go ahead and show that. So I'm going to take my 0.997 atmosphere, 28.2 liter. We're going to divide by 1.3 mole and 0.08206 liter atmosphere per mole Kelvin. And then my other side of the equation is going to be 1.3 mole times 0.08206 liter atmosphere per mole Kelvin times T divided by 1.3 mole times 0.08206 liter atmosphere per mole Kelvin. Now, let's go ahead and get rid of everything that looks the same on the top and the bottom. So there goes my 1.3 moles, and there goes my 0.8206 liters. So now this side only has T left over, and then this side only has just these numbers there. Now let's take a look at the units here. So you got atmospheres, that's going to cancel because you got atmospheres on top, you got atmospheres on the bottom. You also notice that my liter will cancel my liter because there's a liter on top and there's a liter on the bottom. On the denominator, I've got a mole on the top of this division line. So this mole will cancel this mole. So then the only unit that I have not canceled out is my Kelvin. But Kelvin is on the bottom of the denominator. So if it's on the bottom of the denominator, it's really on top of the division line. So I'm going to just go ahead and stick all the numbers into my little calculator. And you know the order that I would do it. You know, I would put that in. You can divide by 1.3, punch the multiply sign and put in the 28.2, and then punch the divide sign and put in the R constant. Now, what I would suggest you do is, you know, if you don't know how to use your own calculator, you're going to get the wrong answer. But I'm going to give you what the final number is going to be, and I'm going to suggest that you make sure that you get the same number when you plug it in into your own calculator so you don't make a little math error and end up with the wrong number. So I'm going to go ahead and crunch those numbers through, and you will see that I get 263.6 Kelvin. And then I'm going to say, all of that cancels out except for the T, so I'm going to say T is equal to 363.4 Kelvin. Now, usually people write the variable on the left side and write the number on the right side. And then you also notice that I only have two significant figures in my number of moles. So I really should only have two significant figures in my Kelvin number. So it should really be, and I'm just going to move my decimal point over and write in scientific notation, it's really 2.6 times 10 to the second Kelvin for my temperature. And there you are. That's the end of that word problem. So this is a relatively straightforward word problem, except for keeping the units consistent, and the tiny bit of algebra is really pretty straightforward. So there you are. The end of that word problem. Okay, let's take another look at or let's take a look at another example. So here's my second example. And what I'm going to do for my second example is, let me go ahead and give you the word problem, and then you can figure out what we're going to do to solve that word problem. So here's my second example. And on my exams, you do know that we do have 15-point word problem. I want to be sure to get these and learn the process of coming up with the correct answer to a word problem. All right, so here's the word problem. If you take a sample of a gas which occupies 1.5 liters at 1.0 atmospheres and 298.14 Kelvin, and transfer the gas to a 0.53 liter tank at 1.2 atmospheres, what will be the new temperature? Okay, so there's my second word problem. All right, so what are you going to do? Well, what you want to do is you want to read the word problem. The most common mistake that people make is they just don't read the word problem and they start trying to plug things in, and then of course you get the wrong answer and you don't even start right. Okay, so let's read the word problem. And let's try to see what kind of information we have given to us and what kind of information we don't have given to us. I'm actually going to stop this problem at this point, and then I'll continue in the next segment.